All right, looks like we have a table of investment growth over years. So it looks like I put $1,000 into the bank. After a year, I have $50 more, and after that, I have like $52.50 more than the previous year, and it grows and it grows and it grows and it grows. Use exponential regression to find an equation that models the account value over time. So I'm going to use exponential regression for this equation right here. Then, if the exponential model from part A is graphed on a semi-log plot, find the equation of the line of you need it for A. So let me go to my calculator and find exponential regression on this guy right here. All right, so exponential regression, we'll start out by doing stat, hitting enter for edit, and plugging our, in this case, our year values into L1. So that's 0, 1, 2, 3, 4, 5. Over in L2, we're going to put our account value. So we have $1,000, then 1,050, 1102.5, 1157.63, 1215.51, and 1276.28. Did I do that right? 76? Those are my numbers. Now, I need to find the equation. I don't need to store the equation because right now for part A, I just care about the equation. So if you've watched my previous videos, we did a lot of storing equations. No need. Hit stat, go to calc, and this is exponential regression. So let's hit up a few times. Exponential regression is 0. So let's just go down to calculate, and hit calculate, and we're going to come up with a really nice equation that we can round wonderfully. A is 1,000.000, so it rounds up to 1,000. And B is 1.05000, so it rounds up to 1.05. So my equation is going to be y equals 1,000 times 1.05 to the x power. Let's go back and write that out. All right, so the equation that I got was rather nice. They want us to use t, so I don't know. I'll just do y equals 1,000 times 1.05 to the t power. Now what I have to do is if the exponential model from part A is graphed on a semi-log plot, find the equation for the line of best fit. The way you find the equation for the line of best fit on a semi-log plot is you write out your exponential equation right there, and you log both sides. So I'm going to log y, and I'm going to log that whole right side. So now I have log of y equals log of 1,000 times 1.05 to the t power. Now I'm doing something times something to the something. If I'm going to expand this, and on the inside I'm multiplying, that must mean I would have been adding to begin with. So this becomes log of 1,000 plus log of 1.05 to the t. Now the last thing I can do is bring that t down because I'm logging it. And so my final answer is going to be log of y equals log of 1,000 plus t log of 1.05. Now what I'm going to do is I'm going to go back to my calculator, find out, it's a shame that number is awful. Find out what log of 1,000 is. I already know it's 3. And find out what log of 1.05 is. That's so close to 0. But then I'm going to use those numbers to finally complete this part B thing right here. So let's go and do that in our calculator. All right, so this part is me just coming up with numbers for the logs. I know back there I said we don't need my calculator for this, but I'm going to. I already said that log of 1,000 is 3. How do I know that? Well, log is log base 10, and 1,000 is 10 to the third. So log base 10 of 10 cancels out, leaving you with a third. Don't believe me? Log of 1,000 is 3. So that's the one number I come up with. The other number that I don't know, but I know is awfully close to 0, is going to be log of 1.05. So log of 1.05, close it, enter, is 0.0211. So we'll round that up to 0.021. So let's use those numbers and plug stuff in. All right, so putting everything together, log base y equals 3 plus 0.021 t. So I guess if we were to try to make that look even more slope-intercept form, we would say log base y equals 0.021 t plus 3. And that is a line of best fit on a semi-log plot. Fun.